Machine learning is the foundation of artificial intelligence, powering everything from fraud detection to recommendation engines, supply chain optimization to predictive healthcare. If you're preparing for a career in ML or aiming to ace your next interview, you've just found the ultimate resource. In this series, we'll cover 200 unique interview-style questions and answers explained in a clear and practical way, just like you'd respond in a real interview. We'll start with the foundations of ML, move through feature engineering, regression, classification, clustering, ensembles, optimization, and finally dive into industry applications, case studies, and the future of ML. By the end, you won't just memorize answers, you'll understand how to think like an ML engineer, explain concepts with confidence, and stand out as a true expert. This is your complete machine learning interview prep guide. Let's get started. What is machine learning, and how is it different from traditional programming? Machine learning is the process where algorithms learn patterns from data instead of being explicitly programmed with rules. In traditional programming, we feed rules plus data into a program to get outputs. In ML, we provide data plus outputs to train a model, and it learns the rules itself. For example, instead of hard-coding spam filters, ML learns from thousands of spam and non-spam emails. This adaptability makes ML powerful for complex, data-rich problems where explicit rules are hard to define. Explain the types of machine learning: supervised, unsupervised, and reinforcement. Supervised learning uses labeled data like predicting house prices from historical sales. Unsupervised learning finds hidden patterns in unlabeled data like clustering customers by shopping behavior. Reinforcement learning is different. An agent learns by trial and error in an environment, receiving rewards or penalties like training a robot to walk or an AI to play chess. These three categories cover most real-world ML problems, each chosen based on data availability and problem type. What are key differences between AI, ML, and data science? AI is the broad field of making machines intelligent. Machine learning is a subset of AI that uses data-driven learning. Data science is the practice of extracting insights from data using statistics, visualization, and ML. For example, I might be building a chatbot. ML is the model that predicts responses, and data science is analyzing conversation logs to improve it. They overlap, but each has its own focus and skill set. What is the difference between parametric and non-parametric models? Parametric models assume a fixed functional form with a limited number of parameters, like linear regression. They're simple, fast, but less flexible. Non-parametric models don't assume a fixed structure. Their complexity grows with data. KNN and decision trees are examples. They adapt better to complex relationships but may require more data and compute. The choice depends on trade-offs between interpretability, flexibility, and resources. What is overfitting, and how can you prevent it? Overfitting happens when a model memorizes training data, performing well there but poorly on new data. It usually indicates the model is too complex relative to available data. Prevention techniques include using more training data, applying regularization like L1 or L2, reducing features, pruning decision trees, or using cross-validation. In practice, it's about balancing complexity with generalization. Models should capture signal, not noise. What is underfitting, and how can you address it? Underfitting occurs when a model is too simple to capture underlying patterns, leading to poor performance on both training and test sets. Causes include using overly basic models, insufficient features, or too much regularization. Solutions include adding relevant features, reducing bias, trying more complex models, or fine-tuning hyperparameters. The goal is to increase model capacity without slipping into overfitting. Explain the bias-variance trade-off in machine learning. Bias is error from simplifying assumptions, while variance is error from sensitivity to training data noise. High bias means underfitting. High variance means overfitting. The trade-off is finding a balance where the model generalizes well. Regularization, cross-validation, and ensemble methods help manage it. In interviews, I often explain it as bias misses patterns, variance chases noise, and the sweet spot is good generalization. What is the curse of dimensionality? The curse of dimensionality refers to the exponential increase in data sparsity as dimensions grow. In high-dimensional spaces, points become far apart, distance metrics lose meaning, and models struggle to learn. For example, KNN becomes unreliable with too many features. Solutions include dimensionality reduction, like PCA, feature selection, or collecting more data. The curse highlights why not all features are useful for learning. What are features, labels, and instances in ML datasets? Features are the input variables like age, income, or location. Labels are the target we want to predict, such as house price or spam/not spam. Instances or examples are individual rows of data combining features and labels. For example, one customer's age, salary, and purchase history is an instance. These terms form the foundation of supervised learning. What is a hypothesis in ML modeling? In ML, a hypothesis is the function the algorithm learns to map inputs to outputs. For linear regression, the hypothesis is a line. For decision trees, it's a set of splits. Training is about searching the hypothesis space for the function that best minimizes error. Essentially, the hypothesis is the model's best guess of how data relationships work. What is the difference between generative and discriminative models? Generative models learn the joint probability distribution P of x, y, and can generate new data points like naive Bayes or Gaussian mixture models. Discriminative models learn the conditional probability P of y given x, focusing on decision boundaries, like logistic regression or SVM. Generative models are useful for simulation and unsupervised tasks, while discriminative models usually perform better in prediction. The choice depends on whether we want to model the data distribution or just the boundaries. Explain lazy versus eager learning in machine learning. Lazy learning delays generalization until prediction time, like KNN, which stores data and computes similarities only when asked. It's simple but slow at inference. Eager learning generalizes during training, like decision trees or logistic regression, so predictions are faster. Lazy learners adapt quickly to new data, but scale poorly, while eager learners invest upfront but deliver efficiency later. What are some common assumptions behind ML models? Assumptions vary by algorithm. Linear regression assumes linearity, independence, and homoscedasticity. Naive Bayes assumes feature independence. KNN assumes nearby points are similar. Many models assume training and test data are drawn from the same distribution. Violating assumptions leads to poor performance, so understanding them helps choose or adjust models appropriately. How do you differentiate between correlation and causation in machine learning? Correlation means two variables move together, but it doesn't imply one causes the other. For example, ice cream sales and drowning deaths correlate due to season, not causation. ML models often capture correlations, but can't establish causality. To test causation, we need controlled experiments, causal inference, or domain knowledge. Misinterpreting correlation as causation can lead to flawed decisions in business or science. What is the difference between online learning and batch learning? Batch learning trains on the entire dataset at once and is retrained periodically like a nightly batch job. Online learning updates the model incrementally as new data arrives, useful for streaming scenarios like stock predictions. Batch is stable and efficient for static data, while online adapts to changing environments. The choice depends on whether data is static or dynamic. What are ML pipelines and why are they important? An ML pipeline automates the workflow from pre-processing to training to evaluation. It ensures repeatability, scalability, and reduces human error. For example, a pipeline might standardize data, apply PCA, train a model, and evaluate metrics, all in sequence. Tools like scikit-learn pipelines or MLflow make deployment consistent. In production, pipelines are critical for reliability. Explain the concept of training, validation, and test sets. The training set is used to fit the model. The validation set tunes hyperparameters and prevents overfitting. The test set evaluates final performance on unseen data. A common split is 70 to 15 to 15 or 80 to 10 to 10. Without proper separation, models may appear to perform well but fail in production due to data leakage. What are hyperparameters versus parameters in ML? Parameters are learned from data during training, like regression coefficients or tree split points. Hyperparameters are set before training and control the learning process, like learning rate, number of neighbors in KNN, or depth of a tree. Parameters define the model, while hyperparameters define how the model is trained. Optimizing hyperparameters is critical for best performance. What are some challenges unique to real-world machine learning versus academic machine learning? In academia, data sets are often clean and well-defined. In the real world, data is messy, incomplete, and constantly changing. Business problems rarely map neatly to standard algorithms. Deployment also introduces concerns: scalability, latency, cost, and compliance. Monitoring drift, handling bias, and securing data are ongoing challenges. Real-world ML isn't just about accuracy, it's about reliability and value delivery. Explain the ML lifecycle from data collection to deployment. The ML lifecycle starts with defining the problem, collecting and cleaning data, and performing feature engineering. Next comes model selection, training, and validation. After evaluation, the model is deployed into production. Post-deployment, monitoring ensures the model performs well over time, detecting drift and retraining as needed. It's not a one-time task, but a continuous loop of improvement. Organizations succeed when they treat ML as an iterative system, not just a model. How do you handle missing values in datasets? Missing values can bias or weaken models if not handled properly. Options include deletion, imputation, or using models that handle missingness natively. For small percentages, row or column deletion may work. Otherwise, imputation methods mean median, mode, KNN imputation, or regression imputation are better. Advanced techniques like MICE or model-based imputation provide more accuracy. The best method depends on why the data is missing, random or systematic. What are categorical encoding techniques? Label, one-hot, target. Categorical variables need encoding to be used in machine learning models. Label encoding assigns numbers to categories, but it introduces unintended order. One-hot encoding creates binary features per category, which works well but increases dimensionality. Target encoding replaces categories with average target values, useful in high cardinality data, but prone to leakage if not cross-validated. The choice depends on algorithm type and dataset size. What are feature scaling techniques? Normalization versus standardization? Normalization scales features to a 0 to 1 range, useful when magnitudes differ, like image pixels. Standardization shifts data to 0 mean and unit variance, making features comparable and improving convergence in gradient-based models. Normalization is sensitive to outliers, while standardization handles them better. Algorithms like KNN or SVM require scaling, while tree-based models don't. What is feature selection and why is it needed? Feature selection reduces irrelevant or redundant variables, improving model accuracy and efficiency. Too many features increase complexity, risk overfitting, and slow down training. Selection methods filter, wrapper, and embedded help keep only the most important ones. Good feature selection enhances generalization, lowers costs, and provides more interpretable models. What are filter, wrapper, and embedded methods for feature selection? Filter methods rank features using statistical tests like correlation or chi-square, independent of models. Wrapper methods evaluate subsets with a chosen model like forward or backward selection, accurate but expensive. Embedded methods select features during model training, like lasso regression or decision tree importance. Each has trade-offs between speed, accuracy, and cost. Often a mix is used in practice. How do you detect multiclinearity in features? Multiclinearity means features are highly correlated, leading to unstable coefficient estimates in regression. Detection methods include correlation matrices, variance inflation factor, or condition number analysis. VIF above 10 signals concern. Remedies include removing one of the correlated features, combining them via PCA, or using regularization like ridge regression. Reducing collinearity improves stability and interpretability. What is dimensionality reduction and why is it important? Dimensionality reduction transforms high-dimensional data into fewer dimensions while retaining essential structure. It's important because high dimensions increase sparsity, computation, and risk of overfitting. Techniques like PCA, LDA, or autoencoders compress data. Benefits include improved visualization, faster training, and noise reduction. In practice, it balances efficiency with explainability. Explain PCA, Principal Component Analysis, and its applications. PCA transforms correlated features into uncorrelated principal components by maximizing variance. Each component is a linear combination of original features. Applications include compressing images, reducing noise, and speeding up models. PCA is unsupervised, so it ignores labels. While powerful, interpretability is reduced. Components don't map neatly to original features. Still, PCA is a standard tool for pre-processing in high-dimensional datasets. What is TSNE, and when would you use it? TSNE is a non-linear dimensionality reduction technique for visualization. It preserves local structure by mapping high-dimensional data into 2D or 3D. It's widely used to visualize embeddings from word models, images, or clustering results. However, TSNE is computationally heavy, non-deterministic, and not ideal for downstream ML tasks. It's best for exploratory analysis rather than production modeling. How do you deal with imbalanced datasets? Imbalance occurs when one class dominates, like fraud detection. Solutions include resampling, oversampling minorities, SMOTE, or undersampling majorities. Algorithm-level methods include adjusting class weights, using cost-sensitive learning, or anomaly detection. Evaluation metrics like F1 score, ROC-AUC, or precision recall curves replace accuracy. The key is ensuring the model learns minority patterns without overfitting noise. What is SMOTE and how is it used? SMOTE, or synthetic minority oversampling technique, generates synthetic samples for minority classes by interpolating between neighbors. It balances datasets without simple duplication. For example, in fraud detection, it creates realistic but new fraud-like cases. While effective, it can introduce noise if applied blindly, so it's often paired with cleaning techniques or combined with undersampling. Explain feature extraction versus feature selection. Feature selection chooses the most relevant existing features, while feature extraction creates new features from transformations. PCA is extraction, lasso is selection. Selection preserves interpretability, while extraction improves efficiency but may lose meaning. Both reduce dimensionality, but the choice depends on whether we prioritize understanding or performance. How do you detect outliers in ML datasets? Outliers can distort training and predictions. Detection methods include statistical tests, z-scores, IQR, visualization, box plots, scatter plots, or ML techniques like isolation forests and DBS-CAN. The decision to remove outliers depends on context. Sometimes they're errors, sometimes they're important signals like fraud. Robust models like tree-based methods often handle outliers better than linear ones. What is the difference between univariate, bivariate, and multivariate analysis? Univariate analysis studies one variable at a time, like histograms of income. Bivariate explores relationships between two variables, like scatter plots of age versus salary. Multivariate examines more than two variables, like correlations in a data set. These analyses reveal distributions, dependencies, and interactions, informing feature engineering and model choice. What is the role of domain knowledge in feature engineering? Domain knowledge guides which features matter, how to transform them, and how to interpret results. For example, in healthcare, BMI may be engineered from height and weight, while in finance, debt-to-income ratio is crucial. Without domain input, ML risks generating irrelevant or misleading features. Domain expertise ensures models are both accurate and actionable. How do you select the right set of features for a model? Feature selection is iterative. Start with exploratory analysis to remove redundant or irrelevant variables. Apply filter methods for correlation checks, wrapper methods for performance-based selection, and embedded methods for model-driven importance. Cross-validation helps ensure stability. The right features are those that maximize generalization while minimizing complexity. What is the difference between PCA and LDA? PCA is unsupervised, maximizing variance without considering labels. LDA is supervised, maximizing class separability by projecting features. PCA is great for visualization or noise reduction, while LDA is stronger for classification problems with labeled data. Both reduce dimensions but optimize different objectives. How do you measure feature importance? Feature importance can be measured through model-based methods like decision tree splits, permutation importance, or regression coefficients. Shapley values in SHAP explain individual feature contributions. Importance scores highlight which features drive predictions, aiding interpretation and selection. Different models may rank features differently, so results should be cross-validated. How do you handle high cardinality categorical features? High cardinality features, like zip codes, create too many dummy variables. Strategies include target encoding, embedding representations, or clustering categories. Hashing tricks also reduce dimensionality. The method depends on model type. The tree-based models handle them better than linear ones. Proper encoding balances information preservation with computational efficiency. What is data leakage, and how do you prevent it? Data leakage happens when information from outside the training dataset sneaks into the model, causing unrealistically good performance but failure in production. Examples include using future data in training or leaking target variables during preprocessing. Prevention includes strict separation of trained test sets, fitting scalars only on training data, and simulating real-world data flow during pipeline building. Awareness and discipline are key. What is linear regression, and what are its assumptions? Linear regression models the relationship between input features and a continuous target by fitting a straight line. It assumes linearity, independence of errors, homoscedasticity, no multicollinearity, and normally distributed residuals. Violating these assumptions can bias results. For example, multicollinearity inflates coefficients, and heteroscedasticity affects standard errors. Despite its simplicity, linear regression is widely used for its interpretability and speed, especially as a baseline model. How do you evaluate the performance of regression models? Regression performance is measured using error metrics. Common ones include mean squared error, MSE, root mean squared error, RMSE, and mean absolute error, MAE. R squared explains the proportion of variance captured, while adjusted R squared accounts for feature count. In practice, RMSE is more interpretable, while R squared shows explanatory power. Cross-validation ensures performance generalizes across datasets. What is multicollinearity, and how does it affect regression? Multicollinearity occurs when features are highly correlated, making it hard to isolate their individual effects. It leads to unstable coefficients. Small changes in data can cause large swings in estimates. Detection methods include correlation matrices and variance inflation factor VIF. To fix it, you can remove redundant variables, use dimensionality reduction like PCA, or apply regularization methods like ridge regression. Explain ridge regression and when to use it. Ridge regression adds an L2 penalty to the loss function, shrinking coefficients toward zero but never to zero. It's ideal when multicollinearity exists or when many small features contribute to the target. Ridge improves stability and reduces variance, though it doesn't eliminate features like lasso. It's best for datasets where you want to keep all predictors but control overfitting. Explain lasso regression and when to use it. Lasso regression uses an L1 penalty, which can shrink some coefficients to zero, performing feature selection. This is valuable when you have many irrelevant features or want a sparse model. Lasso is sensitive to correlated predictors. It may randomly drop one of them. It's best for interpretability and simplifying models, but careful tuning of the regularization strength is required. What is elastic net regression? Elastic net combines L1, lasso, and L2, ridge penalties. It balances feature selection with stability, making it effective when predictors are highly correlated or when the number of features exceeds samples. Elastic net avoids the limitations of pure lasso or ridge by leveraging both penalties. It's widely used in high-dimensional problems like genomics or text-based ML. What is polynomial regression and what are its risks? Polynomial regression extends linear regression by adding polynomial terms of features, allowing curves instead of straight lines. It captures nonlinear relationships well. The risks are overfitting and high variance, especially with high-degree polynomials. Regularization or cross-validation helps manage complexity. While useful, polynomial regression should be applied cautiously and with domain validation. How do you handle heteroscedasticity in regression models? Heteroscedasticity means residuals don't have constant variance, violating regression assumptions. It leads to biased standard errors and unreliable hypothesis tests. Detection methods include plotting residuals or statistical tests like Bruch-Pagan. Fixes include log or box-Cox transformations, weighted least squares, or using robust standard errors. Addressing heteroscedasticity ensures more reliable inference and predictions. What is stepwise regression? Stepwise regression is an automated feature selection technique that iteratively adds or removes variables based on criteria like AIC, BIC, or p-values. It balances model complexity with performance. However, it risks overfitting and can miss optimal subsets. While useful for quick exploration, modern methods like lasso or feature importance are often preferred. What is logistic regression, and how does it differ from linear regression? Logistic regression is used for classification, predicting probabilities between 0 and 1. It applies the sigmoid function to map linear combinations of features into probabilities. Unlike linear regression, which predicts continuous values, logistic regression predicts class membership. It's widely used in binary classification tasks like fraud detection or spam filtering. The key difference is the output type continuous for linear, categorical for logistic. What are odds and log odds in logistic regression? Odds represent the ratio of success to failure probabilities, while log odds are their logarithm. Logistic regression models the log odds as a linear function of features. This ensures outputs map to valid probabilities between 0 and 1. Interpreting coefficients in terms of odds ratios helps explain feature impact in classification tasks like risk modeling. What is the sigmoid function, and why is it used in logistic regression? The sigmoid function squashes real-valued inputs into the open interval 0 to 1, making it suitable for probability estimation. Logistic regression uses it to map linear outputs into probabilities of class membership. Its smooth gradient also enables optimization via gradient descent. While powerful, it suffers from saturation issues at extremes, motivating alternatives in deep learning. But for logistic regression, it's essential. Explain precision. Recall tradeoff in logistic regression. Precision measures correctness among predicted positives, while recall measures coverage of actual positives. Adjusting the classification threshold changes the balance. Lowering it increases recall but reduces precision, and vice versa. In fraud detection, recall might matter more. In medical diagnosis, precision could be prioritized. The trade-off is visualized with precision recall curves. The right balance depends on business context. What is multinomial logistic regression? Multinomial logistic regression extends binary logistic regression to handle multiple classes. It models class probabilities using a softmax function across outcomes. It's widely used in NLP, the example is part of speech tagging, or multi-class classification problems like product category prediction. Unlike one vs rest, multinomial regression models all classes simultaneously. What is ordinal logistic regression? Ordinal logistic regression handles target variables with natural order but unknown spacing like rating scales, poor, fair, good. It assumes proportional odds across categories. This allows modeling rank-based outcomes without treating them as purely numeric or unordered categories. It's widely used in survey analysis and customer satisfaction studies. How do you handle nonlinearity in regression problems? Nonlinearity breaks linear regression assumptions. Solutions include feature transformations, log, polynomial, interaction terms, or using nonlinear algorithms like decision trees. Splines and kernel methods also help capture curves. The choice depends on interpretability, needs transformations. Keep regression simple, while advanced models trade simplicity for accuracy. How do you test regression assumptions? Regression assumptions can be tested via residual analysis. Linearity and homoscedasticity are checked with residual versus fitted plots. Normality of errors is tested with histograms, QQ plots, or Shapiro-Wilk tests. Independence is checked with Durbin-Watson. Multicollinearity is assessed with VIF. Validating assumptions ensures the model's inferences are reliable. What is regularization in regression? Regularization adds penalties to the loss function to prevent overfitting by shrinking coefficients. L1, lasso, drives some coefficients to zero, performing feature selection. L2, ridge, shrinks all coefficients but retains them. Elastic net combines both. Regularization improves generalization, especially in high-dimensional data. How do you interpret regression coefficients? Coefficients represent the expected change in the target for a one-unit increase in a predictor, holding others constant. In linear regression, it's direct. In logistic regression, coefficients are interpreted as log odds changes. Interpretation requires checking scaling, interactions, and multicollinearity, otherwise coefficients may mislead. Context and domain knowledge are essential for meaningful interpretation. What is the difference between R-squared and adjusted R-squared? R-squared measures the proportion of variance explained by the model. However, it always increases when new features are added, even irrelevant ones. Adjusted R-squared penalizes complexity by adjusting for the number of predictors. It only increases if new features improve explanatory power beyond chance. Adjusted R-squared is therefore more reliable for comparing models with different feature sets. Explain the k-nearest neighbors, KNN algorithm. KNN is a simple instance-based algorithm that classifies a point by majority vote of its k-nearest neighbors in the feature space. Distance metrics like Euclidean or Manhattan define closeness. It's non-parametric, meaning it doesn't assume data distribution. While intuitive, KNN is sensitive to scaling, noisy data, and the choice of K. It works well for small datasets but struggles with high-dimensional or large-scale data. What is the curse of dimensionality in KNN? In high dimensions, data points become sparse, and distance metrics lose meaning. Every point looks equally far. This weakens KNN since it relies on distances to define neighborhoods. As dimensions grow, the model becomes computationally heavy and less accurate. Dimensionality reduction, feature selection, or distance-weighted voting helps mitigate this curse. What is a decision tree, and how does it work? A decision tree splits data into branches based on feature values, creating a flowchart-like structure. At each node, it chooses the feature and threshold that best separates classes using criteria like Gini impurity or information gain. The process continues until stopping conditions like max depth or minimum samples are met. Decision trees are interpretable but prone to overfitting, which is why pruning or ensembles are often used. What are Gini impurity and information gain? Both measure node quality in decision trees. Gini impurity calculates the probability of misclassifying a randomly chosen element, while information gain measures reduction in entropy after a split. Gini is computationally simpler, while information gain is rooted in information theory. Many tree algorithms default to Gini, but both typically produce similar results. Explain entropy in decision trees. Entropy measures uncertainty in a dataset. A perfectly mixed dataset has high entropy, while a pure dataset has low entropy. In decision trees, splits are chosen to reduce entropy, called information gain. This ensures each split improves classification by making child nodes purer than the parent. What is pruning in decision trees and why is it needed? Pruning reduces tree size by removing branches that add little predictive power. Without pruning, trees overfit, memorizing noise. Pre-pruning stops growth early with depth or split thresholds. Post-pruning trims a fully grown tree based on validation performance. Pruned trees are simpler, more generalizable, and faster. What are the advantages and disadvantages of decision trees? Advantages include interpretability, handling both categorical and numeric features, and little need for pre-processing. Disadvantages include instability. Small data changes can alter the tree, and overfitting when trees grow too deep. They also struggle with smooth boundaries compared to linear models. Ensembles like random forests solve many of these limitations. Explain naive Bayes and its assumptions. Naive Bayes is a probabilistic classifier based on Bayes' theorem, assuming independence between features. Despite this strong assumption, it works surprisingly well in practice, especially for text classification. It's fast, handles high-dimensional data, and requires little training data. However, correlated features or continuous features without proper distribution assumptions can reduce performance. What is the difference between Gaussian, multinomial, and Bernoulli naive Bayes? Gaussian naive Bayes assumes features follow a normal distribution, useful for continuous data. Multinomial naive Bayes is suited for count data, like word frequencies. Bernoulli naive Bayes handles binary features, like word presence-absence. Choosing the right variant depends on feature type. For example, spam filtering may use multinomial for counts or Bernoulli for binary presence. What is the Bayes theorem, and how is it applied in classification? Bayes' theorem relates conditional probabilities. P of A given B equals P of B given A times P of A divided by P of B. In classification, it calculates the probability of a class given feature values. Naive Bayes simplifies by assuming feature independence, making computation feasible. The class with the highest posterior probability is chosen. This probabilistic foundation gives interpretable predictions and uncertainty estimates. Explains support vector machines, SVMs. SVMs are powerful classifiers that find the hyperplane maximizing the margin between classes. The margin is the distance to the nearest points called support vectors. SVMs handle nonlinear problems using kernel functions. They're robust in high dimensions and effective with small datasets. However, they can be slow with large datasets and sensitive to kernel choice and hyperparameters. What are kernels in SVM? Kernels transform input data into higher dimensional spaces, enabling SVMs to separate classes that aren't linearly separable. Common kernels include linear, polynomial, and RBF, Gaussian. Kernels let SVMs handle complex patterns without explicitly computing high-dimensional mappings. The choice of kernel significantly impacts performance. Explain linear versus nonlinear SVM. Linear SVM uses a straight-line hyperplane to separate classes, suitable when data is linearly separable. Nonlinear SVM uses kernels to project data into higher dimensions, enabling complex boundaries. Linear SVM is faster and interpretable, while nonlinear SVM handles tougher problems but requires more tuning. What is the margin in SVM? The margin is the distance between the decision boundary and the closest data point support vectors. SVM maximizes this margin, ensuring robust classification. Larger margins improve generalization, while smaller margins risk overfitting. This principal maximum margin is the core strength of SVM. What are hard margin versus soft margin SVM? Hard margin SVM strictly separates data with no misclassifications, suitable only when classes are perfectly separable. Soft margin allows some misclassifications by introducing slack variables, balancing margin maximization with tolerance for errors. Soft margin is more practical in real-world noisy data. What is the role of C parameter in SVM? The C parameter controls the trade-off between margin size and classification error. A large C penalizes errors heavily, fitting tightly to data but risking overfitting. A small C allows more slack, producing a wider margin with better generalization. Tuning C is critical for SVM performance. What is the difference between classification and regression ESVM? Classification SVM finds the hyperplane that separates classes, while regression SVM SVR fits a function within an error tolerance epsilon. SVR doesn't try to predict exact values, but ensures predictions fall within a margin of the true outputs. It's useful for problems where small errors are acceptable, like stock trend predictions. What is the ROC curve in classification? The ROC curve plots true positive rate against false positive rate at different thresholds. It shows the trade-off between sensitivity and specificity. A model closer to the top left corner is better. ROC helps compare classifiers beyond a fixed threshold, highlighting overall discrimination ability. What is the AUC score? AUC, or area under the ROC curve, measures overall classifier performance across thresholds. AUC of zero point 0.5 means random guessing, while 1.0 means perfect classification. Higher AUC indicates stronger separation between classes. It's widely used in imbalanced datasets where accuracy is misleading. What is the confusion matrix? A confusion matrix is a table comparing predicted versus actual outcomes. It shows true positives, true negatives, and false negatives. From it, we calculate accuracy, precision, recall, and F1 score. It's the foundation for evaluating classification models and understanding their strengths and weaknesses across classes. What is clustering, and how is it different from classification? Clustering groups data into clusters based on similarity without predefined labels. Classification, on the other hand, requires labeled data to train a supervised model. For example, clustering might group customers by purchasing habits, while classification predicts if a transaction is fraud or not. Clustering is unsupervised and exploratory, often used for segmentation, anomaly detection, and pattern discovery. Explain the k-means clustering algorithm. K-means partitions data into k-clusters by minimizing within cluster variance. It starts with random centroids, assigns points to the nearest centroid, then updates centroids iteratively until convergence. It's simple, scalable, and effective when clusters are spherical and similar in size. However, it requires specifying k beforehand and struggles with irregular or overlapping clusters. Initialization also affects results, making methods like k-means useful. How do you choose the optimal k in k-means? Common methods include the elbow method, where you plot inertia versus k and look for the elbow point. The silhouette score measures how well points fit within clusters, higher being better. The gap statistic compares clustering performance against random baselines. Often, a combination of these methods, along with domain knowledge, gives the best estimate of k. What are the limitations of k-means clustering? K-means assumes clusters are spherical and equally sized, which rarely holds in real-world data. It's sensitive to outliers and initialization, may converge to local minima, and requires knowing k in advance. It also performs poorly with categorical features. For irregular clusters, density-based methods like DBSC-AN are often better. Explain hierarchical clustering. Hierarchical clustering builds nested clusters in either agglomerative bottom-up or divisive top-down fashion. Agglomerative starts with individual points and merges them step by step, while divisive starts with all points and splits them. Results are visualized using a dendrogram. Unlike k-means, it doesn't require specifying k, but it's computationally expensive for large datasets. What are dendrograms in clustering? A dendrogram is a tree-like diagram that shows how clusters are merged or split at each step in hierarchical clustering. The y-axis represents distance or similarity between clusters. Cutting the dendrogram at a chosen height gives the desired number of clusters. It's a useful visualization for deciding k. What is db-scan and how does it work? db-scan is a density-based clustering method. It groups together points with high density and marks sparse regions as noise. Two parameters, epsilon radius and min-PTs, minimum neighbors, define density. db-scan discovers clusters of arbitrary shape, unlike k-means, and automatically identifies outliers. However, it struggles with varying density and requires careful parameter tuning. Compare k-means versus db-scan. K-means is centroid-based, assumes spherical clusters, and requires k. db-scan is density-based, finds arbitrary shapes, and doesn't need k. K-means works well for balanced, clean data, while db-scan is better for noisy data and irregular clusters. However, db-scan requires tuning epsilon and min-pts carefully, while k-means is simpler and more scalable. What is Gaussian mixture model GMM clustering? GMM assumes data is generated from a mixture of Gaussian distributions. Each cluster is represented by a Gaussian with its own mean and covariance. Unlike k-means, GMM performs soft clustering, assigning probabilities of belonging to each cluster. It's more flexible for elliptical clusters, but computationally heavier. GMM uses the expectation maximization algorithm for parameter estimation. What is expectation maximization, EM? EM is an iterative optimization technique used to estimate parameters in models with latent variables, like GMMS. The expectation step estimates cluster membership probabilities, and the maximization step updates distribution parameters. It repeats until convergence. EM is powerful but sensitive to initialization and may converge to local optima. What is anomaly detection in ML? Anomaly detection identifies unusual data points that don't conform to expected patterns. It's used in fraud detection, network security, and predictive maintenance. Techniques include statistical methods, clustering-based detection, or isolation forests. The challenge is that anomalies are rare and diverse, making supervised labeling difficult. Unsupervised methods are common in this domain. What are distance metrics used in clustering? Euclidean, Manhattan, Cosine. Distance metrics define similarity. Euclidean measures straight-line distance, common in continuous data. Manhattan calculates distance along grid lines, useful for sparse features. Cosine similarity measures the angle between vectors, ideal for text or high-dimensional data. Choosing the right metric greatly impacts clustering results, depending on data structure and domain. What is cluster evaluation and what metrics are used? Since clustering is unsupervised, evaluation is tricky. Internal metrics like silhouette score, Davies-Bolden index, and Kalinsky-Harabas index assess compactness and separation. External metrics, when ground truth exists, include adjusted RAN index or mutual information. Visualization is also key for practical validation. Explain silhouette score in clustering. Silhouette score measures how well a point fits into its cluster compared to others. It ranges from -1 to 1, where values close to 1 indicate well-clustered data, 0 indicates overlapping clusters, and negative means possible misclassification. It's widely used for selecting the best K. What is dimensionality reduction, and how does it relate to clustering? Dimensionality reduction, like PCA or TSNE, simplifies high-dimensional data into fewer dimensions while preserving structure. This improves clustering by removing noise, reducing sparsity, and making distances meaningful again. It also aids visualization. Without dimensionality reduction, clustering in high-dimensional spaces often suffers due to the curse of dimensionality. What is spectral clustering? Spectral clustering uses eigenvalues of a similarity matrix to project data into lower dimensions before applying k-means. It's powerful for non-convex or graph-structured data, like community detection in networks. While effective, it's computationally expensive and less scalable for large datasets. How does clustering help in recommendation systems? Clustering groups users with similar behaviors or items with similar features. Recommendations can then be made by suggesting items liked by members of the same cluster. For example, in e-commerce, clustering customers by browsing habits helps personalize suggestions. It's a simple, interpretable baseline for recommendations before moving to advanced collaborative filtering. What is soft clustering versus hard clustering? Hard clustering assigns each point to exactly one cluster, like k-means. Soft clustering assigns probabilities of belonging to each cluster, like GMM. Soft clustering is more flexible for overlapping data, but harder to interpret. Hard clustering is simpler and faster, but less realistic when boundaries are fuzzy. What are the applications of unsupervised learning in industry? Unsupervised learning is used for customer segmentation, fraud detection, market basket analysis, gene expression grouping, and anomaly detection and security. It's valuable when labels are unavailable or costly. By revealing hidden structures, unsupervised methods help businesses uncover opportunities and risks that wouldn't be visible through supervised approaches alone. How do you visualize high-dimensional clusters? Visualization methods include PCA, TSNE, or UMAP, which reduce dimensions to 2D or 3D for plotting. Cluster assignments can be colored to reveal separation. Heat maps, dendrograms, or pair plots also help. Effective visualization validates clustering results and communicates findings to stakeholders who may not understand metrics. What is ensemble learning? Ensemble learning combines multiple models to create a stronger overall predictor. The idea is that diverse models, when aggregated, reduce variance, bias, or noise compared to individual learners. For example, random forests combine decision trees, and boosting methods combine weak learners sequentially. Ensembles usually outperform single models, especially in competitions and real-world production systems. What is bagging? Bagging, or bootstrap aggregating, trains multiple models on different bootstrap samples of the dataset and averages their predictions. It reduces variance and prevents overfitting. Random forest is a classic bagging algorithm. Bagging works best with high variance, low bias models like decision trees, stabilizing them through aggregation. What is boosting? Boosting builds models sequentially, where each new model focuses on correcting the errors of the previous one. Instead of training models independently, boosting combines weak learners into a strong ensemble. Algorithms like AdaBoost, gradient boosting, and XGBoost fall in this category. Boosting often achieves higher accuracy than bagging, but can be more prone to overfitting if not tuned properly. Compare bagging versus boosting. Bagging reduces variance by training models in parallel on random subsets, then averaging predictions. Boosting reduces bias by training sequentially, with each learner focusing on errors of the last. Bagging is robust and stable, while boosting often yields higher accuracy but requires careful tuning. In practice, bagging is safer for noisy data, while boosting excels in structured datasets. What is random forest and how does it work? Random forest is an ensemble of decision trees built using bagging. Each tree is trained on a bootstrap sample, and splits are chosen from random subsets of features. This randomness decorrelates trees, improving generalization. Predictions are made by majority vote, classification, or averaging, regression. Random forest is robust, interpretable, and widely used in industry. What are the advantages of random forests? Random forests handle both classification and regression, reduce overfitting, and provide feature importance. They're less sensitive to outliers and scaling compared to other models. They work well with default parameters, making them a reliable go-to model. The main drawback is slower inference compared to single trees. What is feature importance in random forest? Feature importance measures how much each feature contributes to reducing impurity across all trees. It can be calculated using Gini importance or permutation importance. While useful, feature importance may be biased toward high cardinality features. Still, it's a valuable tool for interpretability and feature selection. Explain AdaBoost and its working. AdaBoost, or adaptive boosting, builds weak learners sequentially, adjusting weights of misclassified samples to focus the next learner on harder cases. Final predictions are a weighted vote of all learners. AdaBoost often uses shallow decision trees as base learners. It's effective but sensitive to noisy data and outliers since weights can overemphasize difficult points. What is gradient boosting? Gradient boosting builds trees sequentially, where each new tree corrects errors by fitting the gradient of the loss function. Unlike AdaBoost, which adjusts sample weights, gradient boosting optimizes directly via gradient descent. It's highly flexible, able to minimize different loss functions, and forms the foundation for XGBoost and LightGBM. Proper tuning of learning rate and tree depth is key. Explain XGBoost and why it's popular. XGBoost, or Extreme Gradient Boosting, is an optimized gradient boosting library. It's popular because it's fast, scalable, and includes regularization, missing value handling, and parallelization. It consistently delivers top performance in Kaggle competitions and industry applications. The trade-off is complexity. XGBoost requires careful hyperparameter tuning for best results. What is LightGBM, and how is it different from XGBoost? LightGBM is a gradient boosting framework designed for speed and efficiency. Unlike XGBoost, which grows trees depth first, LightGBM uses leaf-wise growth with depth limits, producing more accurate splits. It handles large datasets better and supports categorical features natively. However, it can overfit small datasets if not tuned. It's ideal for big data ML tasks. What is CatBoost and what makes it unique? CatBoost is another gradient boosting algorithm, notable for handling categorical features efficiently without heavy preprocessing. It reduces overfitting via ordered boosting and requires minimal tuning. It's robust across different domains, making it beginner-friendly. Cat Boost is often preferred when data sets have many categorical variables. What is stacking in ensemble learning? Stacking combines predictions from multiple base models by training a meta model on their outputs. Unlike bagging or boosting, stacking blends diverse algorithms like combining support vector machines, trees, and logistic regression. The meta-learner learns how to best weight-based models. Stacking often boosts accuracy, but increases complexity and risk of overfitting. What are blending techniques in ensembles? Blending is similar to stacking, but uses a holdout validation set instead of cross-validation to train the meta model. It's simpler and faster, but less data efficient. Blending is often used in competitions for quick model combination. While easier, stacking is generally more robust due to cross-validation. What is bagging classifier versus random forest? A bagging classifier is a generic ensemble method applying bagging to any base learner. Random forest is a specific bagging method using decision trees with feature randomness. Random forest is essentially bagging plus feature subspace sampling, making it more decorrelated and powerful. Bagging is general, while random forest is specialized. What are weak learners in ensemble methods? Weak learners are models that perform slightly better than random guessing. In ensembles, multiple weak learners combine into a strong model. For example, AdaBoost uses shallow decision stumps as weak learners. Individually weak, together they create a high-performing predictor. Why do ensemble methods reduce variance? Variance comes from sensitivity to training data. By combining multiple models, ensembles average out noise from individual models. For example, random forest reduces variance by aggregating many decision trees. This stabilizes predictions and improves generalization. Variance reduction is the core strength of bagging methods. What is feature bagging? Feature bagging, or random subspace method, trains models on random subsets of features instead of samples. It reduces correlation between learners, improving ensemble performance. Random forest combines feature bagging with bootstrap sampling, enhancing diversity. How do you tune hyperparameters in ensemble models? Hyperparameter tuning involves grid search, random search, or Bayesian optimization. Key parameters include the number of estimators, tree depth, learning rate, and regularization strength. For random forest, focus on tree count and max features. For boosting, learning rate and depth are critical. Cross-validation ensures tuning balances bias, variance, and efficiency. What are some real-world applications of ensemble methods? Ensembles power fraud detection in finance, churn prediction in telecom, credit scoring in banking, and click-through prediction in advertising. In healthcare, ensembles improve disease prediction accuracy. Kaggle competitions often feature ensembles for winning solutions. Their ability to balance accuracy, robustness, and generalization makes them a staple in production ML systems. What is cross-validation and why is it used? Cross-validation evaluates model performance by splitting data into multiple folds. The model trains on some folds and validates on others, rotating until all folds are used. This gives a more reliable estimate than a single train test split. It reduces variance in performance metrics and ensures models generalize well. It's especially useful when data is limited. What is k-fold cross-validation? In k-fold cross-validation, data is split into k equal folds. The model trains on k-1 folds and validates on the remaining fold, repeating k times. Results are averaged for a stable performance estimate. Common values of k are 5 or 10. The trade-off is between bias and variance. Higher k gives lower bias but higher computational cost. What is stratified cross-validation? Stratified cross-validation ensures that each fold preserves the class distribution of the dataset. It's crucial for imbalance classification, where random splits may distort class ratios. Stratification ensures each fold is representative, giving fairer and more consistent evaluation. It's the standard approach for classification problems. What is leave one out cross-validation, LOOCV? LOOCV is an extreme form of k-fold cross-validation, where k equals the dataset size. Each iteration trains on all but one data point and tests on the excluded point. It provides an almost unbiased performance estimate, but is computationally expensive for large datasets. It's most useful for small datasets where every sample matters. What are training, validation, and test splits? The training set fits the model. The validation set tunes hyperparameters and helps prevent overfitting. The test set measures final performance on unseen data. A common split is 70-15, 15 or 80-10-10. Keeping strict separation avoids data leakage and ensures reliable performance estimates. What are performance metrics for classification? Key metrics include accuracy, precision, recall, F1 score, RO, CAUC, and log loss. Accuracy works for balanced data sets, while precision recall and F1 are better for imbalanced cases. ROCAUC measures overall discrimination ability, while log loss penalizes incorrect probabilities. The right metric depends on business goals. Explain precision, recall, and F1 score. Precision is the proportion of true positives among predicted positives. Recall is the proportion of true positives among actual positives. F1 score is their harmonic mean, balancing precision and recall. For example, in fraud detection, recall ensures catching more frauds, while precision avoids false alarms. F1 is ideal when both matter. What is specificity versus sensitivity? Sensitivity, or recall, measures how well positives are identified. Specificity measures how well negatives are correctly classified. For example, in medical tests, sensitivity ensures few false negatives, while specificity ensures few false positives. Both are important depending on the application's tolerance for error. What is Matthews correlation coefficient, MCC? MCC is a balanced metric that considers true or false positives and negatives, giving a correlation coefficient between predicted and actual labels. It's robust for imbalanced data sets, unlike accuracy. Values range from -1, total disagreement, to 1, perfect prediction. MCC is common in bioinformatics and other sensitive domains. Explain ROC curve and AUC. The ROC curve plots true positive rate versus false positive rate at different thresholds. AUC measures the area under the curve, summarizing performance across thresholds. AUC of 0.5 means random guessing, while 1.0 is perfect classification. It's widely used to compare models beyond a fixed threshold. What is log loss in classification? Log loss, or cross-entropy loss, measures the accuracy of predicted probabilities. It penalizes confident but wrong predictions more heavily. A lower log loss means better calibrated probabilities. It's particularly important when probability estimates, not just class labels, matter, like in risk scoring or medical predictions. What is mean squared error, MSE? MSE is the average of squared differences between predictions and actual values in regression. Squaring penalizes larger errors more, making it sensitive to outliers. It's widely used for optimization but less interpretable than MAE. RMSE is often used to bring units back to the original scale. What is mean absolute error, MAE? ME is the average absolute difference between predictions and true values. It treats all errors equally, making it more robust to outliers than MSE. While less sensitive to extreme errors, it may underestimate their impact. It's a straightforward metric for regression tasks. What is RMSE, root mean squared error? RMSE is the square root of MSE, bringing error units back to the original scale of the target variable. It penalizes large errors more heavily, making it useful when big mistakes are costly. RMSE is often the preferred metric in forecasting tasks. What is R-squared score? R-squared measures how much variance in the target is explained by the model. A value of 1 indicates perfect fit, 0 means no better than mean prediction, and negative values indicate worse performance. Adjusted R-squared corrects for feature count, making it more reliable for model comparison. How do you evaluate clustering algorithms? Clustering lacks labels, so evaluation uses internal metrics like silhouette score, Davies-Boldon index, or Kalinsky-Haribas index. If ground truth exists, external metrics like adjusted RAND index are applied. Visualization tools like TS and ePlots also help validate cluster quality. What are internal versus external evaluation metrics? Internal metrics, like silhouette score, Evaluate clustering quality without ground truth by measuring compactness and separation. External metrics, like adjusted RAND index, compare clustering results to known labels. Internal metrics are for unsupervised tasks, while external ones are for benchmarking. What is holdout validation? Holdout validation splits the dataset into train and test sets once, without folds. It's simple and fast, but can give unstable estimates depending on the split. It's often used for quick checks or when datasets are very large. What is bootstrap sampling in validation? Bootstrap sampling repeatedly samples data with replacement to create multiple training sets. Models are evaluated across these resampled datasets, and results are averaged. It provides robust error estimates, especially when datasets are small. Bagging ensembles also rely on bootstrap sampling. What is early stopping and why is it used? Early stopping halts training when validation performance stops improving, preventing overfitting. While often discussed in deep learning, it applies to boosting and other iterative models too. By monitoring validation metrics, training stops before the model memorizes noise. It's a simple but powerful form of regularization. What is gradient descent? Gradient descent is an optimization algorithm that minimizes a cost function by iteratively adjusting parameters in the opposite direction of the gradient. Think of it as rolling downhill toward the lowest point. It's widely used in regression, SVMs, and boosting. The step size, or learning rate, controls how fast it converges. Too small, it's slow. Too large, it overshoots. What are types of gradient descent? Batch, mini-batch, stochastic. Batch gradient descent uses the entire dataset to compute gradients, stable but slow. Stochastic gradient descent, SGD, updates parameters for each sample. Fast but noisy. Mini-batch gradient descent finds a middle ground, updating with small batches, combining efficiency with stability. Most modern algorithms use mini-batch as it balances convergence speed and generalization. What is the learning rate in optimization? The learning rate controls the step size in gradient descent. A high rate speeds learning but risks divergence, while a low rate ensures stability but can be painfully slow. Tuning it properly is critical, often using learning rate schedules or adaptive optimizers that adjust rates dynamically. What is momentum in gradient descent? Momentum accelerates gradient descent by adding a fraction of the previous update to the current one. This smooths out oscillations and speeds convergence, especially in ravines where gradients point in different directions. It's like pushing a ball downhill. Once moving, it keeps rolling. Momentum helps avoid local minima and improves efficiency. What is Nesterov accelerated gradient, NAG? NAG improves momentum by calculating gradients at the look-ahead position instead of the current one. This provides a corrective adjustment, preventing overshooting. It often converges faster and more reliably than standard momentum. NAG is widely used in advanced optimizers where precision and speed both matter. What is Adigrad optimizer? Adigrad adapts the learning rate for each parameter based on historical gradients. Features with frequent updates get smaller steps, while rare features get larger steps. It's great for sparse data like text or clickstream data. However, learning rates shrink continuously, sometimes stopping progress prematurely. What is RMS prop optimizer? RMS prop improves Adigrad by using a moving average of squared gradients to prevent the learning rate from shrinking too much. It works well in non-stationary problems like reinforcement learning. By balancing updates, RMS prop maintains steady progress without vanishing step sizes. What is Atom optimizer? Atom combines momentum, first moment estimates, and RMS prop, second moment estimates. It adapts learning rates per parameter while keeping progress smooth. It's efficient, requires little tuning, and works well across diverse tasks. Atom has become the default optimizer in many ML frameworks, though sometimes SGD with momentum generalizes better in large-scale problems. Compare Atom versus SGD. SGD with momentum is simple, robust, and often yields better generalization, but it requires careful tuning. Atom is adaptive and converges faster with less tuning, especially on noisy problems. However, Atom sometimes overfits and plateaus, while SGD continues improving. The choice depends on task size, complexity, and tolerance for tuning effort. What is a cost function in ML? A cost function, or loss function, quantifies the difference between predicted and actual outputs. For regression, it might be MSE. For classification, cross-entropy. Optimization aims to minimize this cost. Choosing the right cost function ensures the model learns the right objective for the business problem. What are convex versus non-convex functions? Convex functions have one global minimum, making optimization straightforward. Gradient descent always finds the best solution. Non-convex functions have multiple local minima, making optimization harder. Many machine learning problems, especially in high dimensions, are non-convex. Techniques like random restarts or advanced optimizers help escape poor minima. What is regularization and why is it needed? Regularization penalizes model complexity to prevent overfitting. It discourages large coefficients by adding penalty terms to the loss function. This forces the model to focus on generalizable patterns instead of memorizing noise. Common methods include L1, L2, elastic net, and early stopping. Regularization is essential in high-dimensional or noisy datasets. Compare L1 versus L2 regularization. L1, lasso, adds absolute values of coefficients as a penalty, shrinking some to zero, performing feature selection. L2, ridge, adds squared coefficients, shrinking all but keeping them non-zero. L1 is good for sparse models. L2 is better for multicollinearity. Elastic net combines both for balance control. What is dropout and why is it used in ML, non-DL context? Dropout randomly drops features during training, forcing the model to rely on multiple signals instead of specific ones. While popular in deep learning, the idea applies in traditional ML as a way to reduce overdependence on certain features. It acts like feature bagging. Improving robustness. What is weight decay in regularization? Weight decay is another term for L2 regularization, where large weights are penalized to keep the model simple. By shrinking weights, it prevents overfitting and improves stability. It's commonly used in regression and optimization algorithms. What is early stopping as a regularization method? Early stopping halts training when validation performance stops improving, preventing overfitting. Instead of letting the model learn noise in the later iterations, training is cut short. It's simple, effective, and widely used in iterative algorithms like boosting. How does feature selection act as regularization? By removing irrelevant or redundant features, feature selection reduces complexity and variance. This is a form of implicit regularization since simpler models are less prone to overfitting. Techniques like lasso or tree-based importance directly combine selection with learning. What is the role of penalty terms and cost functions? Penalty terms discourage overly complex models by adding constraints to the cost function. L1 and L2 penalties shrink coefficients, while elastic net blends both. These penalties help balance model fit and simplicity, improving generalization. What is the difference between bias and variance in optimization? Bias is systematic error from simplifying assumptions, while variance is error from sensitivity to training data. In optimization, high bias means the model underfits, high variance means it overfits. Regularization and proper optimization balance both to achieve generalization. How do you detect overregularization? Overregularization happens when penalties are too strong, making the model underfit. Signs include high bias, low variance, and poor training performance. Detection involves monitoring both training and validation errors. If both are high, the model is too constrained. Reducing penalties or adding complexity fixes this. What is semi-supervised learning? Semi-supervised learning uses a mix of labeled and unlabeled data. Since labeling is expensive, this approach leverages large unlabeled datasets with a small labeled subset. Algorithms propagate label information or use pseudo-labeling. For example, in medical imaging, a few expert-labeled scans guide the learning of thousands of unlabeled ones. It reduces cost while improving accuracy compared to unsupervised learning. What is self-supervised learning? Self-supervised learning generates labels automatically from data itself. The model learns auxiliary tasks, like predicting missing parts, which help build strong representations. Though more common in deep learning, the concept applies in classical ML too, like predicting masked features or rotations. It bridges the gap between supervised and unsupervised learning, turning raw data into supervision at scale. What is active learning? Active learning reduces labeling effort by letting the model choose the most informative samples to label. For example, in fraud detection, the model flags uncertain transactions for expert review. This way, fewer labels are needed for strong performance. Query strategies include uncertainty, sampling, query by committee, and expected model change. Active learning is practical in domains where data is abundant, but labels are costly. What is online learning and where is it used? Online learning updates models incrementally as new data arrives instead of retraining from scratch. It's useful in streaming applications like stock predictions, recommendation engines, or fraud detection. Algorithms must be efficient, adaptive, and robust to concept drift. Online learning keeps models fresh in dynamic environments. What is transfer learning in non-deep ML? Transfer learning reuses knowledge from one problem to improve performance on a related problem. In non-deep ML, this could mean reusing engineered features, learned embeddings, or pre-trained models like clustering results. For example, customer segmentation learned in one market might transfer to another with slight adjustments. It reduces data needs and training time. What is meta-learning in ML? Meta-learning, or learning to learn, aims to train models that quickly adapt to new tasks with limited data. It focuses on finding patterns in how models learn, not just what they predict. In classical ML, meta-learning appears in hyperparameter tuning, algorithm selection, and ensemble stacking. It's particularly valuable in AUML, where the system decides the best approach automatically. What is reinforcement learning at a high level? Reinforcement learning trains an agent to act in an environment by maximizing cumulative rewards. The agent observes a state, takes an action, and receives feedback. Over time, it learns policies that maximize long-term gains. Though more associated with robotics and games, the concept also influences adaptive decision-making in finance and operations research. What is multitask learning? Multitask learning trains a model to solve multiple related tasks simultaneously, sharing representations between them. For instance, a model might predict both credit risk and likelihood of churn from customer data. Shared knowledge improves generalization, especially when tasks are correlated. It reduces overfitting and makes efficient use of data. What is concept drift? Concept drift occurs when the statistical properties of target variables change over time. For example, customer behavior shifts or fraud tactics evolve, making old models less effective. Drift can be sudden, gradual, or recurring. Detecting drift involves monitoring performance and distributions. Addressing it requires retraining, adaptive learning, or online models. What is model interpretability and why is it important? Model interpretability explains how models make predictions. It's important for trust, debugging, and compliance in regulated industries. Simple models like linear regression are inherently interpretable, while complex ensembles require tools like SHAP or LIME. Without interpretability, stakeholders may reject even highly accurate models, especially in healthcare or finance. What is SHAP in model explainability? SHAP, or Shapley Additive Explanations, assigns each feature a contribution score for individual predictions. Rooted in game theory, SHAP is consistent and interpretable. For example, in loan approvals, SHAP can show how income, credit score, and debt-to-income ratio influence the decision. It's widely used for transparency in black box models. What is LIME and model interpretability? LIME, or Local Interpretable Model Agnostic Explanations, explains predictions by approximating a complex model with a simple interpretable one around a given instance. For example, it might fit a local linear model to explain why a particular transaction was flagged as fraud. LIME is intuitive, but can be unstable depending on sampling. What is causal inference in ML? Causal inference goes beyond correlation, aiming to identify cause-effect relationships. Techniques include randomized controlled trials, instrumental variables, and causal graphs. In ML, methods like causal forests or counterfactual reasoning are emerging. For example, causal inference can reveal whether a marketing campaign actually caused increased sales or just correlated with seasonal trends. What is the difference between supervised anomaly detection and unsupervised anomaly detection? Supervised anomaly detection uses labeled normal and anomalous data to train classifiers. It's accurate but requires labeled anomalies, which are rare. Unsupervised methods assume anomalies deviate significantly from majority patterns, using clustering or distance metrics. Semi-supervised methods use only normal data. In practice, unsupervised approaches are more common due to scarcity of anomaly labels. What is AutoML and what are its advantages and limitations? AutoML automates the ML pipeline, including pre-processing, feature engineering, model selection, and tuning. Advantages are speed, accessibility for non-experts, and strong baseline performance. Limitations include reduced control, potential overfitting, and lack of deep interpretability. AutoML is best for rapid prototyping, but expert oversight ensures results align with business goals. How is ML used in finance for fraud detection? Fraud detection uses machine learning to spot unusual patterns in transactions. Supervised models learn from historical fraud cases, while unsupervised models flag anomalies in real time. Features may include transaction amount, location, and frequency. Ensemble methods and anomaly detection algorithms are common. The challenge is balancing high recall to catch frauds without overwhelming false positives that annoy legitimate customers. How is ML applied in healthcare diagnostics? ML supports diagnostics by analyzing patient data, lab results, and imaging. Models classify conditions, predict disease risks, or recommend treatments. For example, logistic regression may assess diabetes risk, while ensemble methods predict survival outcomes. The key is interpretability. Healthcare requires models to explain predictions for doctors' trust and regulatory compliance. What role does ML play in recommendation systems? ML powers recommendations by learning user preferences from historical interactions. Algorithms include collaborative filtering, matrix factorization, and clustering. For example, e-commerce platforms suggest products similar to past purchases, while streaming services recommend shows based on viewing habits. Accuracy improves engagement and revenue, but balancing diversity and avoiding filter bubbles is critical. How does ML power search engines? Search engines use machine learning for ranking, query understanding, and personalization. Models learn from click-through data to improve relevance. Clustering and embeddings help interpret queries, while ranking models optimize page ordering. ML also detects spam and ensures high-quality results. The constant challenge is scalability and handling ambiguous or long-tail queries. How does ML impact supply chain optimization? ML forecasts demand, optimizes inventory, and predicts supply chain risks. Regression models forecast sales, while classification models predict supplier reliability. Reinforcement and online learning adapt to real-time logistics. Companies use ML to cut costs, reduce waste, and improve efficiency in global supply chains. How does ML improve personalized marketing? ML segments customers, predicts purchase intent, and personalizes campaigns. Classification models identify likely buyers, while clustering reveals customer groups. Recommendation systems suggest tailored products. By analyzing behavioral and demographic data, ML enables precision targeting, increasing conversion rates and ROI compared to generic campaigns. How is ML used in credit scoring? Credit scoring models predict default risk based on applicant data income, credit history, spending patterns. Logistic regression, decision trees, and ensemble models are commonly used. ML improves accuracy beyond traditional scoring, but transparency is vital due to regulatory oversight. Explainable ML ensures fair and compliant credit decisions. How does ML help in predictive maintenance? Predictive maintenance uses machine learning to forecast equipment failures before they occur. Models analyze sensor data like vibration, temperature, and usage. Classification models flag potential failures, while regression predicts time to failure. This prevents costly downtime, reduces maintenance costs, and extends equipment life. Real-world examples include aviation, manufacturing, and energy. How does ML support anomaly detection in cybersecurity? In cybersecurity, ML detects unusual behavior in network traffic or user activity. Unsupervised models like isolation forests or DBS can identify anomalies, while supervised models classify known threats. ML scales better than rule-based systems, adapting to evolving attacks. The challenge is balancing sensitivity to detect threats without flooding analysts with false alarms. What are ML applications in retail and e-commerce? Retail uses ML for demand forecasting, price optimization, recommendation engines, and customer segmentation. E-commerce platforms apply machine learning for personalized search, fraud prevention, and inventory management. For example, Amazon recommends products based on user activity, while supermarkets optimize stocking with ML-based demand prediction. How is ML applied in energy demand forecasting? ML predicts energy demand by analyzing weather, historical usage, and economic factors. Regression models forecast consumption, while time series ML models handle fluctuations. Accurate forecasts reduce waste, balance supply, and support renewable integration. Utilities rely on ML for smarter grid management. How does ML support manufacturing optimization? ML optimizes manufacturing by predicting defects, adjusting process parameters, and improving quality control. Classification models detect faulty products, while regression predicts production yield. Predictive maintenance ensures machines run smoothly. ML reduces downtime, lowers costs, and improves product consistency, making it central to Industry 4.0. How is ML used in insurance risk modeling? Insurers use ML to predict claim probabilities and assess customer risk. Models analyze demographics, driving history, or health records. Logistic regression, gradient boosting, and random forests are common. ML allows dynamic pricing and fraud detection, but requires transparency to meet regulatory standards in insurance. How is ML used in sentiment analysis, non-NLP features, example tabular? While sentiment analysis is often NLP-driven, ML can use non-text features like review length, rating distribution, or engagement metrics. Classification models combine these structured features with text-based ones. For example, analyzing metadata of reviews can improve sentiment predictions. This hybrid approach enhances robustness when textual data is noisy. How does ML enable dynamic pricing? Dynamic pricing adjusts prices in real time based on demand, competition, and customer behavior. Regression models forecast demand, while classification models identify customer willingness to pay. Airlines, ride-hailing apps, and e-commerce platforms rely on ML-driven pricing to maximize revenue. Ethical concerns arise if pricing becomes discriminatory, so fairness is critical. Walk through how you would build a model for predicting housing prices. I'd start with problem definition. Predicting continuous values makes this a regression task. Data collection would include features like square footage, location, age, and amenities. Next, I'd perform exploratory analysis to check distributions, missing values, and correlations. Feature engineering might add ratios like price per square foot. Models like linear regression or random forest regression would be tested. I'd evaluate with RMSE or R squared using cross-validation to ensure robustness. Finally, I'd deploy the best model in a pipeline, monitoring for drift as housing markets change. How would you design an ML pipeline for detecting fraudulent transactions? Fraud detection requires both accuracy and speed. I'd begin by gathering labeled transaction data, engineering features like transaction frequency, location changes, or merchant categories. Because fraud data is imbalanced, I'd handle it with techniques like SMOTE or cost-sensitive learning. Ensemble models such as random forest or gradient boosting would be strong candidates. Metrics like precision, recall, and AUC are critical since false negatives are costly. The pipeline must support real-time scoring with continuous retraining as fraud patterns evolve. How would you evaluate an ML model for predicting medical outcomes? Medical prediction models demand both accuracy and fairness. I'd use metrics like precision, recall, specificity, and ROC-AUC, focusing on minimizing false negatives. Cross-validation ensures stability. Calibration curves are important since doctors rely on well-calibrated probabilities. Interpretability tools like SHAP or LIME help explain decisions to clinicians. Finally, I'd validate with domain experts and ensure compliance with regulatory standards like HIPAA. How would you handle a dataset with 90% negative and 10% positive labels? That's an imbalanced dataset. Accuracy would be misleading, so I'd focus on precision, recall, F1 score, and ROCAUC. Resampling methods like SMOTE or undersampling, the majority class can balance data. Alternatively, I'd use class weighting or anomaly detection algorithms. Ensemble models often handle imbalance better. The key is aligning evaluation with business needs, catching as many positives as possible without too many false alarms. How would you deploy an ML model in a low latency environment? Low latency requires optimization beyond accuracy. I'd start by selecting lightweight models or distilling complex models into simpler versions. Pre-processing must be efficient using feature stores or pre-computed transformations. For deployment, I'd consider containerization with Docker, orchestration with Kubernetes, and serving via REST APIs or gRPC. Monitoring latency and throughput is as critical as accuracy. Edge deployment may also be considered if data transfer delays are significant. What is the future of auto ML in industry? Auto ML is set to expand by automating end-to-end pipelines, data cleaning, feature engineering, model tuning, and even deployment. This lowers the barrier for non-experts, making ML accessible across industries. However, auto ML won't replace experts, it augments them by handling repetitive tasks, letting data scientists focus on strategy and interpretability. Its biggest growth will be in small to mid businesses and rapid prototyping. How will explainable ML influence adoption in regulated industries? Explainability is critical in industries like healthcare, finance, and insurance, where black box models face resistance. Tools like SHAP, LIME, and interpretable ensembles allow stakeholders to understand predictions. This transparency builds trust, satisfies regulators, and reduces bias risks. In the future, explainability will shift from optional to mandatory, driving adoption of ML in sensitive domains. What is the role of hybrid ML systems combining symbolic plus statistical methods? Hybrid systems blend symbolic AI's reasoning with statistical ML's pattern recognition. Symbolic approaches bring logic, rules, and interpretability, while statistical ML offers flexibility and scalability. For example, combining rule-based medical guidelines with ML-based diagnosis models creates systems that are accurate yet trustworthy. Hybrid ML will likely dominate in domains where both structure and uncertainty must be managed. How is federated ML shaping privacy-preserving applications? Federated ML trains models across distributed devices without centralizing data. Each device learns locally, sharing only model updates, preserving privacy. It's especially valuable in healthcare, banking, and mobile devices where data is sensitive. Challenges include communication overhead and handling non-IID data. With stronger encryption and differential privacy, federated ML will become the backbone of privacy-first AI solutions. What are the biggest open challenges in classical machine learning today? Even with deep learning's rise, classical ML faces challenges in scalability, handling high-dimensional sparse data, and robustness against noisy or adversarial inputs. Interpretability, fairness, and bias remain unresolved issues. Additionally, bridging the gap between academic benchmarks and messy real-world data is ongoing. Ensuring ML systems are explainable, fair, and adaptable will be the next frontier for classical ML. You've just explored 200 unique machine learning interview questions and answers covering everything from foundations and algorithms to real-world applications and future trends. By now, you should not only know the answers, but also how to explain them in a way that shows confidence, clarity, and expertise. Remember, interviews are not about memorizing definitions. They're about demonstrating how you think, how you solve problems, and how you apply ML in practice. Keep practicing, keep questioning, and keep building. Machine learning is one of the fastest growing fields in tech, and your preparation today is your edge tomorrow. If this guide helped you, share it with others preparing for ML roles. And if you're watching on YouTube, don't forget to subscribe for more deep dive interview prep on generative AI, NLP, computer vision, and beyond. Stay curious, stay consistent, and go ace that interview.